This is chapter 15, all about lipids. So we're going to talk about those. So a lipid is a biomolecule, so just a biological molecule. It contains either a fatty acid or a steroid nucleus, and a nucleus I want you to think about as being the center. So it either has a fatty acid kind of center area or a steroid center. Lipids are soluble in organic solvents but not in water. So I want you to think about lipids coming from the word fat in Greek, lipos. And that's what they are, right? These are the essentially the fats that we need to survive. And so a really important lipid in your cells is your cell membrane. And then you've also got steroids, which are hormones that we need to survive. And so we're going to talk about the different categories of this. This chapter is kind of large, and I'm going to try to break it down to where I only want you to recognize certain things in the chapter. And so I will be going through and kind of thinning this out as we go and telling you, like, I want the slides to be available for you for if you move on to other classes. You have the information available when you go into nursing programs or whatever. But for your exam for this, we're going to focus on kind of just definitions of things, and I give you a picture and you tell me what it is. I'm not going to make you draw these really complicated molecules. I'm not going to have you go into like super complicated reactions. It's just going to be very kind of, okay, is this a steroid, right? And so we'll talk about that. And so you've got two types of lipids, okay? Lipids can give you other molecules. So you've got things like waxes, fats, and oils, phospholipids. They're esters. And so you should be familiar with an ester. That's why our last week with organic chemistry is really helpful here, because it's not a new thing, a new word to give you an ester. And they can be hydrolyzed, meaning hydrolysis. And so you should be thinking, oh yeah, I know about the hydrolysis of esters. There's an acid hydrolysis and there's saponification, a base hydrolysis. And that's where we use water to separate the ester into two parts. You get the actual acid part, and then you get the rest of it, right? And typically with an ester, it's the alcohol part. So there are some lipids that are esters, and then there are some lipids that don't contain any fatty acids, and so therefore they cannot make the fat. They don't have the fatty acids in them, so they're not esters. We call these steroids, and you cannot break them apart into fatty acids because they don't have that. So there's kind of two types. We got your fatty acids over here. So if you look at if you look at this section here, and this should be familiar to you, this is a carboxylic acid group, and then you've got this long chain, because this is a hydrophobic area, okay? Then this would be your fatty acid. You've got this nonpolar region, and then you've got this little polar region. Now this nonpolar region is way too long for the polar region to do anything, and so this long chain fatty acid would not dissolve in water. And so you think about like a fat, greasy kind of thing that's not going to dissolve in water. And then you've got your steroid. Now steroids are always categorized by this as their nucleus. You can hang things off of them and have other pieces around it, but you have to have this core here to be considered a steroid. So what you're going to look for are these fused carbon rings, and we'll get more into exactly what's going on here. But so for this chapter, we need to be able to identify, is it a steroid or is it a fatty acid lipid? And so this is a really great flow chart because it breaks everything down for you. And again, I will be just kind of giving you pictures of things and asking you, okay, which of the following, what is this thing? And you'll have A, B, C, D, E, like what is a wax, Triacylglycerol, Glycerophospholipid, or a Sphingomyelin, and you can kind of look and see what you notice. And again, the organic chemistry is going to be really helpful to you in this. And so we're going to go through all of these in the chapter. But you've got waxes. So if you are a fatty acid, right? If you're a steroid, then you kind of are just a steroid, right? But if you're a fatty acid, you can be broken down into a wax, okay, which is a long chain alcohol bonded with a fatty acid. Remember, we said this was an ester, right? And so you have an alcohol bonded with a carboxylic acid that gives you an ester. You've got your triacylglycerols, which are glycerols, your backbone. Remember from glycerol, I think you've seen that in the previous chapter. It's got these 3 alcohol groups hanging off of it. Well, we connect those 3 alcohol groups to 3 different fatty acids, and we get 3 different like ester regions here. These are held together with ester linkages. Then you've got your glycerophospholipids, and if you look at the word phospholipid, you think, oh, that probably has some phosphorus in it. Yeah, it's got a phosphate. So you have your triacylglycerols that have 3 fatty acids. So every alcohol part of glycerol is a fatty acid. Then you've got a glycerol backbone with 2 fatty acids and 1 phosphate group with an amino alcohol connected to the phosphate. So 2 fatty acids and a phosphate connected to your glycerol backbone. And then you got this really weird thing called a sphingolipid. And the sphingo sign is this kind of molecule that will make like a kind of a sideways L shape. It'll only have 1 fatty acid and a phosphate group here. And so if you can kind of remember this flow chart and maybe print this one out as a good way to identify them, that's what I'll be asking you to do. Okay, so this is asking you to tell not which type with all 3 of these, which type goes with A. So it contains a fused 4-membered ring system. Remember, that is your steroid. Contains a long carbon chains. That's going to be your fatty acid. And then contains carbonyl groups. That's going to be your ester groups, right? Those carbonyl carbons, those are going to be your fatty acids. And so these are the types of questions you're going to need to be responsible for. Again, if you look at the speaker's notes of the slides, you'll see if there's a learning check where I don't really want you to worry about doing that, I'll write do not need for exam in the speaker's notes. Alright, so try this one. Which of the following is not a characteristic of liquids? So this is a multiple choice question. So the answer here is C. Lipids are nonpolar. So lipids, I want you to think about fat. If you've ever gotten any sort of like animal fat, okay, and grease on you, any sort of fatty acid, I'm thinking like, we think of them as oils, kind of, right? And that does not dissolve in water because it's mostly nonpolar. And it may contain a carboxylic acid group, right, if it's a fatty acid. It may contain a forming structure if it's a steroid, but it definitely is not soluble in water. So let's dig in a little bit into your fatty acids. You may think of saturated fatty acids, unsaturated fatty acids, and we're going to go through all of that. And you know the difference between saturated and unsaturated as far as carbon chains go. And so that is not going to change. We're just going to have degrees of unsaturation. So they're telling you here to think about like this. Saturated fatty acids would be kind of all stacking together. And then if you get unsaturated fatty acids, you get these kind of kinks in the chains with these double bonds or maybe triple bonds hanging out in there, and then you kind of get this kind of shape. And so your unsaturated fatty acids don't really fit together as well, which means their intermolecular forces, their forces of attraction, are not quite as strong. So you'll see them more as a liquid, kind of flowing, like olive oil. And then you'll see your saturated fats as more solids. Right, so if you're thinking of a solid fat that you might cook with. And so fatty acids are, they have a carboxylic acid group within, that's how we call them fatty acids, but then they have this long unbranched carbon chains. Typically your carbon chains are 12 to 18 carbon atoms long, and so this means that we're totally overpowering that polar carboxylic acid side. So this whole thing is going to be nonpolar. The long carbon chain is what's causing that nonpolarity and insolubility in water. They're saturated if they don't contain a double bond, and they're unsaturated when they do contain a double bond, and you know them. So when you're drawing a fatty acid out, you should be familiar with how to draw line angle, how to draw condensed. But notice this other condensed here. So I'll kind of zoom into this. And so if you're looking at this this new condensed here, instead of doing CH2, CH2, CH2 10 times, you would just write CH2 with a little 10 on the outside of a parentheses, because this tells me, hey, this is like a repeating unit, and instead of writing it all the way out, I could just put it like this. So you do need to recognize it as this. Now, I'm not going to have you memorize all of the different fatty acids, but you should know that a long chain of carbons, you can write it like this as kind of a shorthand. And you should recognize the carboxylic acid group on the end. You're going to see a lot of them look like line angle formulas though, because that takes up a lot less space and you actually get to see all the carbons. And so if you have saturated, you have only single bonds. And so here are some examples of saturated fats. We got lauric acid in coconut oil. So we get these more solid. And then you've got stearic acid in animal fat, palmitic acid in palm. And then this ratio here is important because it tells you how many carbon atoms you have and how many double bonds you have. And so we consider this like a factor of saturation. So if you have 12 carbon atoms and 1 double bond, then you know that you're a little unsaturated. But if you have 12 carbon atoms and 3 double bonds, then you're more unsaturated, so you'll have a different shape. And you can actually tell how many H's you'll have just based on the number of carbons and based on how many bonds you know you have. I'm not going to ask you to go into that much detail with it, but just recognizing that these are fatty acids, and these are saturated, meaning they don't have any double bonds. And if you look at their melting points, they have melting points that range 44 degrees Celsius up to 63, 69 degrees Celsius. And so for most people, room temperature is like 25, 23, 20, sometimes if we're in a cold room, degrees Celsius. And so these things are going to be solid at room temperature, but then you put them, maybe if you're using coconut oil to cook with or something, and it's going to melt. Then we get a monounsaturated fatty acid. So think about what you think that means. Monounsaturated means one place of unsaturation. So look here at the double bond ratio. So you got 16 carbons, 1 double bond. Monounsaturated. So I would expect to be able to give you a number like this and say, hey, this ratio here is telling me the number of carbons and the number of double bonds. This would be a monounsaturated fatty acid if I gave you that information. And so you get much lower melting points. So you see the difference here. If we look back at one that has 16, this one has 18. So let's see here. Here's palm oil, has a melting point of 63. And if I add 1 double bond, just 1, I go from a melting point of 63 to a melting point of 0, meaning that this has the same melting point as water. So that changes a lot. All I changed was I put 1 double bond in there. And so that really changes how well it's connected to each other. That 1 double bond creates this kink here, and you can see it in the line structure. And now it can't fit quite like those Pringles chips like it used to. Like all of these can really fit on top of each other in this nice order, which makes them more strongly held together. These London dispersion forces are very strong when you stack them. Which means they're held together tighter and their melting points are higher, versus one kink totally messes that up and it's going to have a much lower melting point, so it's not held together quite as much. And then you have oleic acid, which is present in olive oil, which you all know is a liquid at room temperature as well. And then we have polyunsaturated. So you know poly means many, so you've got many, more than one. So you have 1 unsaturation, so 1 double bond, monounsaturated. Or if you have 2 or more, just call it poly. We don't need to say diunsaturated, triunsaturated. Just call it polyunsaturated. And then your melting points, as you see, our melting points go way down. The more unsaturation you have, the less likely you are to have any sort of significant attraction to the other molecules of your kind, and you're more easily separated or melted or boiled, right? So you can see all of these double bonds hanging out in here. And of course, if you have a double bond, then you get cis and trans, right? And you may have heard of trans fats. Well, trans fats are just double bonds in fatty acids where the rest of the carbon chain continues in a trans position. And so if you look here, you see the cis position, meaning that the main part of the fatty acid is on this side of the double bond, and the other main part is on this side of the double bond. So we're really looking at that. Now, to make it a little easier, you can just look at the hydrogens, because the hydrogens will be opposite of the rest of the chain, right? And so if you look at your hydrogens, you can tell pretty easily if it's cis or trans. Just draw those hydrogens out, kind of take your, so they have your line angle formula here. We're kind of breaking that rule of line angle and really kind of spelling it out for ourselves to see if it's cis or trans. Also, if you look at just the line angle of this, you can kind of tell as well. So we have this cis, meaning both sides of the double bond for our important groups, and then we have this trans. Now, the trans one, it's really easy to look at the hydrogens, a little harder to look at the rest of it because it kind of looks like it's kind of in this like straight line, right? So be careful with it. If you do need to just break it open and put your carbons and hydrogens in, it's easier to see with the hydrogens than it is with the rest of the molecule. Almost all of them have one or more cis double bonds, and you'll see that they'll kind of kink in this way, and that just is something that we find. But you can have both orientations, of course. So these would be geometric isomers because they are structurally all connected in the same way. It's just that where that you can't rotate around that double bond, and so you have to decide which side the rest of the compound is going to go. So we have some essential fatty acids that we need. They must be obtained from our diet, and so we call them essential because you have to have them in order to survive. And so it's not that you should not eat things that are fatty acids because they're fat and that's bad. Like, actually, we can make some of them, but there are a lot of them that we cannot synthesize, we can't make, and so you have to eat them. So here's what I was talking about, how if you have your saturated, we can fit together like those Pringles chips. We can fit these together. And so what kind of forces do I get? I get London dispersion forces all through here. Why London dispersion? Well, you have three main forces of attraction, right? We have hydrogen bonding, which we know over here we can do hydrogen bonding, right? These all can have hydrogen bonding with each other. But because the most of the molecule is all of these nonpolar covalent hydrogen carbon bonds, I get these London dispersion forces. So these are London dispersions. For a review on that, check out the end of chapter 6. So the more they're stackable, the more dispersion forces you get. The better your glue is, the harder you are to pull apart. So you are usually a solid at room temperature. In unsaturated, again, we look at these bending and try to put these together. So that's what they've done in this picture. So like, okay, try to put stearic acid together. Great. It stacks right on top of each other just like Pringles chips. But then take those same chips, or maybe these are not the stackable ones, right? And then you try to put them together like oleic acid. We try to stick it together and we get this hodgepodge of crazy, like, things that are kind of attracted to each other, maybe repelled from each other, and it makes it look very fluid, right? So that should help you think about the state of matter that this is. This is olive oil, and so it's and this is animal fat. So we have a solid fat and we have a liquid fat. So do a quick learning check and we'll just kind of go through these together. Why is this molecule an acid? So what part of it behaves as an acid? So hopefully your eyes are roaming over here to the carboxylic acid group. And so if I were to say, hey, treat this as an acid, what would it do? You would say, oh, well, it would donate H+, right? We would get rid of that. So that would be why it's an acid, because it has an H to donate here. How many total carbons? Well, we can count here 1, 2, 3, 4, and then you would actually add up all of these carbons here. So 4 plus 7 plus 7. You can get yourself an answer from adding that up. Is this saturated, monounsaturated, or polyunsaturated? Well, I only see one double bond, so it is monounsaturated. It's not saturated because it does not have all single bonds. Saturated, single bonds. Is it likely to be solid or liquid at room temperature? Again, we get one double bond and it's probably a solid. That's how big of a difference it makes. It's probably a solid. Would it be soluble in water? No, because look how long these carbon-hydrogen chains are. This tiny little polar part can't really, make up for all of that. So if you're looking for the answer here, it's 18. We're adding all that up. It's a monounsaturated, it's liquid, and it makes it insoluble. Prostaglandins, they're hormone-like substances, and they're things that we need to lower or raise blood pressure, do contracting of smooth muscles in the uterus. So you have to have these hormone-like substances, and they are made from essential fatty acids that you need. Prostaglandins, you've got these guys that reduce inflammation and pain in an area. And so we can see here's the acid that I need to take in to make these things here. They produce inflammation and pain, and so the analgesic that you take to help that stops the substance from being produced. So non-steroidal anti-inflammatory drugs that actually block the production of these, and that decreases the pain and inflammation. And so why does your body produce these things? It's to help heal the area, right? But it's also painful. So if you can block those things from being made, then you're blocking the inflammation and the pain there. And so you can go for it. Identify functional groups and all these things if you want to have a ball looking at all the functional groups here. But definitely still make sure that you're practicing naming those and finding those guides. What about omega-3s? We talk about that all the time. Ooh, fish oil is good for you because it's got omega-3 fatty acids. So omega-3s, oh wow, my picture is really bad. Omega-3s are unsaturated. They're polyunsaturated. And that means they have more than one double bond. And so when you're talking about omega-3s, omega-6s, it's the first double bond occurring at carbon-6. And so if you're looking at, you're always counting from, we're actually counting from the methyl end of the carbon chain if you're talking about your double bonds. So you got omega-6s, you got omega-3s, and it's kind of hard to see. But if you look, we're actually counting from the other end for your fatty acids. So omega-3s would be your first double bond occurring at carbon-3. And again, you do not need to know these. It's just information for you to have. If you're going to be in the healthcare field, you're going to probably talk to patients about omega-6, omega-3s, and just knowing what that means. Oh, it means, an unsaturated, a polyunsaturated fatty acid. So cold water fish are a good source of omega-3s. Again, here's a better picture of those if you wanted to have them, if you're interested. And then you can, a lot of these are really common names, or names. I'm not going to have you do the IUPAC names for these. You could figure them out if you wanted to, but I'm not going to have you work on those. So, omega-3 fatty acids actually lower the tendency of blood platelets to stick together, and so it kind of lubricates your blood platelets in a good way, meaning that they're not going to form that plaque and adhere. They're not going to be sticky. You do not have to know this. I'm not going to have you memorize the name. Now, I will show you a picture. I would say like, oh, here is the picture of this fatty acid. Is it saturated, unsaturated, or unsaturated, polyunsaturated? And then you would tell me, but I'm not going to have you memorize like certain fatty acids. So if you want to look up an image of these and then try to tell, then you can do a learning check for that, but I'm not going to have you do that. All right, so waxes. Beeswax is an example. waxes are very waterproof. They're very hydrophobic. And so we use waxes on coatings of things to make sure water doesn't get in. We also use waxes to help keep water out of places, but also to keep water in places. So waxes specifically are esters of saturated fatty acids and long chain alcohols. So you've got a long chain fatty acid on one side, and you got a long chain alcohol on the other side, and then you know how we make esters, esterification, right? So we have our fatty acid, and that OH leaves with an H from the alcohol, and we make water. That's a dehydration. And then you get an ester bond. And so if you see a fatty acid, kind of long carbon chain, an ester bond, and then a little alcohol chain over here, then you've got a wax. Now, are you going to see an OH? No, you're going to see an ester for a wax. But on one side comes from the fatty acid, just like every ester, and the other side comes from an alcohol, just like every ester. It's just now we're going to be talking about 14 to 30 carbons instead of like 5 carbons on each side, okay? And a lot of plants use waxes on their leaves so that the water doesn't get out. So here are some waxes, and we can see that ester right here, and that's what I want you to recognize. Like, I will give you an image, and I'll say, is this a wax? Is this a fatty acid? Is this like, what is this? And you'll say, oh, this is a wax because it's got this ester, this one ester piece right here. And you can see you've got a long carbon chain of this alcohol. So what would be the alcohol that would make this ester? Well, we cut it here and you stick an H here. So it would be 29 CH2s, 1 CH3, and an OH. That would be the alcohol. What would the carboxylic acid be? What would the fatty acid be that made this? Well, we cut it here, right? Add an OH, and then you'd have 14 CH2s and a CH3. Like, you could draw that out, knowing from what you know from organic chemistry. If you've ever used carnauba wax or jojoba, this is what those look like. Triacylglycerols. So fatty acids in our bodies are stored as triglycerides. Triacylglycerols, that's the fancy name for it. We call them, typically, you will call them in the healthcare field, triglycerides. They are esters, okay? Just like the wax is kind of a simple version of this. They are esters. They're an ester, though, of a glycerol. And we've seen a glycerol before. A glycerol is like a chain of carbons where each carbon has an alcohol group on it. So it's like these 3 carbons and they all have alcohols. So imagine that every alcohol also has an availability to make an ester. And so you connect a fatty acid to each one of those alcohols in glycerol and you get a triglyceride, right? And you can name them by chaining the word glycerol to glycerol. We got a glycerol group, and naming the fatty acid as carboxylates. Again, I'm not going to have you name the whole thing. I would just have you recognize like what it is. So here's an example, and you can see we're putting this glycerol. You should be able to recognize this glycerol as being a 3-carbon chain with an OH on each carbon. And then you get your OH from your carboxylic acid chain of your fatty acid, whatever fatty acid that you're using. And then we're doing that dehydration, right? We make 3 waters, and you get your ester bonds. Okay? And so if you do this to all 3 places, you get a triglycerate, or a triacylglycerol, fancy, but it's the same thing that you would be telling a patient, like, oh, you need to look at your triglycerides. Same thing. So if we have stearic acid, we change it to tristerin, right, or glycerol tristerate, and it's a common name. I'm not going to have you worry about the names. But if you wanted to break up, like say a patient had too many triglycerides and you needed to break up some of them, right, you could maybe turn them back into fatty acids. And there's a lot of different reactions we can do with every one of these ester bonds as a reactive place in this molecule. You can have a mixed triglyceride. You can have different fatty acids come in. don't worry about remembering all the names of these fatty acids. You can have saturated and unsaturated kind of hanging out together because there's a place of reaction for every OH group in that glycerol molecule. They're a great place to store energy, and so when you're thinking about storing fat, that's how you store it. Because that ester group is really reactive, it's easy to break that bond, right? And to then take those molecules apart and use them as fuel. Animals that hibernate are eating lots and lots of these kinds of things because they innately kind of know that that's what they need to survive. And so the fat that's stored, their body is using during hibernation. Again, you do not need to know the fatty acids individually. If you really want to, go for it, but I'm not going to ask you to identify these. I would ask you to identify that this molecule is a triacylglycerol or a triglyceride. And I would expect you to know that this is a monounsaturated fatty acid because it has one double bond. I'm not going to have you draw the structure from the name. I'm not going to have you name the structure, but you should be able to recognize, like if I said, which of the following is a triacylglycerol, and I gave you a bunch of different images, you would say, well, this one, because it's got a glycerol group with 3 fatty acids hooked to it, right? And these are all what kind of saturation? These are all mono, one double bond, unsaturated. Now here they're telling me that this, if I give you this, you can kind of draw it if you really think about it, because this is telling me how many carbons there are. So there's 14. Whoops. So there's 14 carbons, and how many double bonds? No double bonds. So can you draw a fatty acid with 14 carbons and no double bonds? Sure you can. It's just a carboxylic acid with 14 carbons. Go for it. You could draw that. Could you put that in with a glycerol molecule? Yes, you could. I may throw in a bonus question or something at some point where we do a little bit of this practice with something where I give you this number. But again, I'm not going to focus on you drawing or naming these guys. Okay. So here you get your 12, 13, 14, and we're going to connect them just like we would make an ester out of each of those OHs. And so typically we call things that are solid at room temperature, which remember are your saturated or unsaturated. Solid at room temperature is typically your saturated. These are your Pringle chips fitting close together, right? So we usually call those fats. And we usually call something that's a liquid at room temperature an oil, right? But it's all kind of the same thing. It's just versus saturated versus unsaturated. So unsaturated fats, we call it usually oils. But you can have, you can have saturated and unsaturated of either one of these. You can have unsaturation from oils. But then they might be those oils that kind of go back and forth between liquid and solid, right? Like thinking of coconut oil, how easy it is to melt these, right? And if you have mostly saturated fatty acids, then, you're going to be more likely to be room temp solid, like coconut oil. Again, we talked about the melting points already. We have higher melting points. The more easily we can stack, the higher our melting point's going to be. And so they actually have a breakdown of the percentage of saturated and unsaturated fatty acids in the fats and oils that we're making, these triglycerides. So olive oil is not just oleic acid, right? It's got a lot of it's got some other things in it too, but it's mostly unsaturated. If you're looking at things that are mostly saturated, look how these things are mostly saturated, so mostly blue, we got solid stuff, right? If you're mostly poly and monounsaturated, then you're liquid, and that should make sense. You can actually, you know this, right? Can you take a double bond and turn it into a single bond? Can you take something saturated or unsaturated and saturate it? Yeah, we add hydrogen, right? You know how to do this. You can take an unsaturated double bond to anything, and you can do hydrogen with a catalyst, right? Hydrogenation, and turn it into a total single bond thing. And so you can turn those oils into solid fats. And so this is something that should be familiar to you, right? And so we see these double bonds here in our fat turning into single bonds. And so you're going to get a totally different molecule, different thing. I'm not going to have you do these reactions out, but I may still ask you to do, a double bond go into single bonds in a more less complicated form. Now, also with double bonds, you can make alcohols, right? We can do this is hydrogenation. This is just the same thing they just talked about. They're just continuing to go with this. And we do this in commercial hydrogenation. So businesses will do this with the oils to turn them into solids. I'm not going to have you, again, memorize all of these things, but I may have you do like a small part, like here's a double bonded compound. What would the hydrogenation be? And so again, here are the cis and trans, kind of looking at those together. And so, trans fatty acids behave more like saturated fatty acids, because they are stackable, right? Versus the cis ones are the ones that give us like the hard like kinks, but it's the trans ones that they actually will stack better. And so they kind of behave more like saturated, like single bonded ones. And so if you take a cis fatty acid and you break that and you wanted to turn it into a trans fatty acid, you'd have to be very careful and remove that hydrogen in a specific way. But I'm not going to ask you to know that. So trans fatty acids, you can find that in milk, eggs, beef. And then you have trans fats from a process of hydrogenation commercially, and you get all like deep fried foods, these kinds of things that are commercially produced. You have natural trans fats. It's the ones that come from these types of foods that there was a big like stink about, oh, no trans fats anymore, and you're not allowed to have trans fats in things. Like a trans fat is just more saturated, or it's not more saturated, but it acts more like saturated, so it winds up being a little more solid in your body, right? Tighter held together in your body, and so that can be bad for like atherosclerosis. And so if you want to try a little true or false, go for it. There are more unsaturated fats in vegetable oils. Well, if it's an oil, there's got to be more unsaturated fat in it because it's a liquid, right? Vegetable oils have higher melting points than fats. Well, fats are solid, then oils are not solid, then they don't have higher melting points. Hydrogenation of oils convert some cis bonds to trans double bonds. True. So if you do hydrogenation, it's not gonna always go exactly the way you want it. Like sometimes you can actually get some trans out of it as well. And animal fats have more saturated fats because they're more solid. And so here's a practice, draw the condensed structure I'm not going to ask you to go through and do that, and just recognize that this is a hydrogenation is fine. Again, we're just taking our double bonds and getting rid of them. So hydrolysis, this is what we're going to do if we wanted to like make glycerol again and we wanted to make the carboxylic acid again. So like if you want glycerol and your fatty acid back from your triacylglyceride, your triglyceride, then you could hydrolyze it, right? You can separate it, lyse it, just like we would get rid of an ester. It's exactly the same thing. We can do this with an acid, okay, or a digestive enzyme called lipase. Or we can do this with a base, and we're going to do this as a lab. We're actually going to make soap. And so if you take this triglyceride fat and you lyse that ester bond with a strong base, you get sodium salts of the fatty acids, just like you get sodium salts of carboxylic acid. This is the process of forming the soap. The soap is a salt of the fatty acid. And we use lye for that. Or if you want to give a softer liquid soap, you can use something like potassium hydroxide. And we're going to be using the ones that give us some shapes, some sodium hydroxide. So here's the reaction we're going to be doing to make our soaps. This should be very similar to what you are used to seeing from last week. And so here's just a small chart of all the things you can do with the lipid reactions here. Again, I'm not going to have you write this reaction out. If you want to try to cut it and see what you make, go for it. I'm not going to have you do this on an exam. I may just have you recognize that this is a hydrolysis, right? And this is the acid hydrolysis, not the saponification one, because it's lipase or in a strong acid. So this is the one where you actually get the carboxylic acid back, right, and the glycerol back. All right, so moving on to phospholipids. Phospholipids have phosphate. So if you have a triacylglycerol, right, so triacyl group here, then you have your phospholipid. It's the same glycerol backbone, but you have a phosphate instead of a fatty acid. On the other side of that phosphate, you still have your alcohol, but it's an amino alcohol. And so you've got two different types of phospholipids, Glycerophospholipids and the Sphingomyelin. So your glycerophospholipids are with glycerol, right? You've got two fatty acids, and then the very bottom one, you have an ester with a phosphoric acid, which is called a phosphoester bond, and you get an amino alcohol. A sphingomyelin contains a sphingosine instead of a glycerol, so it's this weird, it's a kind of a L-shaped, an upside-down L-shaped molecule, and it's only got one fatty acid. So you can recognize the difference in these. If you do have a phosphate group, then you have one fatty acid, or you got two fatty acids. And you should also recognize the glycerol backbone. An amino alcohol. So what should you see in an amino alcohol? Well, we should see a nitrogen group, and we should see an alcohol group. And so we get a nitrogen group here, and this is an ammonium nitrogen, so a nitrogen plus. And then we have an OH somewhere else in the molecule. Now, can you also get like other pieces? Sure, but you have to have an alcohol and you gotta have a nitrogen, and the nitrogens are typically always ionized to a positive ion. So that is what an amino alcohol is. Again, I'm not going to have you name these, memorize them, know that they're at a pH of 7.4. Like, I just want you to know that it's a thing. What is it? You should be able to tell it has two parts, an amino part and an alcohol part, and you should know what that means. So here are two glycerophospholipids. We get them in egg yolk, wheat germ, yeast. So you can see the phosphate group here making this ester bond. So instead of a carbonyl group, we get a phosphate group here. And then we have your alcohol, your amino alcohol part. So it's just the same as the alcohol part. You get kind of two alcohol parts. We got the glycerol, which is the alcohol part. Then we get this phospho part, and then you have the other alcohol part. It's on this side, so it's kind of like two alcohols together. So again, with all of these, we've got polar and nonpolar regions. We got a polar head, This ionized amino alcohol right here, this is polar. It's got a little charge on it, so it's a partial positive charge, so it's got a polar end. It's in the phosphate portion, including this whole section right here, is very attracted to water. And then you've got all this hydrocarbon tail that's got these long fatty acid chains, right? And this is going to be really important when we start to build cell membranes. And so we see this all kind of drawn out. What we find is that these groups don't like each other, right? Because this group is more polar. This side is more polar. This side is more non-polar, and so they kind of don't like each other. So we get this thing. We get this phosphate amino alcohol end on this side, and we get this non-polar end. So we call this the head, and we call this the tail because it's got these long carbons kind of training. So we'll say this is the polar head of the phospholipid, and we've got this non-polar tail of the phospholipid. So it's a very simplified way of looking at it, but that's kind of how you should think about it because that's how we're going to make cell membranes. Snake venom has this. They hydrolyze, so they break apart phospholipids with they lyse phospholipids in red blood cells, so they break apart all of the cell membranes in your red blood cells. So again, I will not have you memorize these names, but if I gave you pictures of these, you should be able to tell me what it is. And so you can, if you want to look up pictures of those, you can. Again, I'm not going to have you draw the structural formula of them because I'm not going to have you memorize the names, but if I gave you the pieces, could you maybe draw it or put it together? Like, I would be very helpful in trying to give you that information. Maybe do a little bit of matching on this exam too. So a sphingomyelin, in a sphingomyelin, the amine group of the sphingosine forms an amide bond to the fatty acid. And so it's not a glycerol base at all. Now we're something totally different. We don't have a glycerol base. The hydroxyl group of the sphingomyelin forms an ester bond. So we get an amide bond and we get an ester bond. They're in the myelin sheath. Okay, and so if you have studied anatomy, and I'm not sure if you probably covered this in physiology too, the myelin, so think about sphingomyelin as myelin sheath. That's the coating around the nerve cell. And so what this does is insulates the nerve cell and allows the nerve impulses to move quicker. And so these are really important molecules. So you can see the difference. Like this kind of looks like a glycerol backbone, but if you look, it actually keeps going, and it's not an ester here like we normally see. We see this kind of continuation. So I want you to think about this is your sphingosine here. So recognizing that and how it's different from a glycerol backbone is really helpful in identifying this. And then it actually has a little amino end that then makes this amide with your carboxylic acid fatty acid, and then you get your phosphate group with your amino alcohol kind of thing going on. So it's kind of like a combination of everything that you learned this sphingomyelin. And so they want you to try to draw it. Again, I might give you the pieces and have you kind of put it together. But again, we can see here's this sphingosine group. And then we have an amide group here. And then we have our phosphate and our amino alcohol. All right. That was all about fatty acids. Now we're going to talk about steroids. So steroids, we got cholesterol, bile salts, and hormones. So a steroid has 3 cyclohexane rings. A cyclohexane means 6 carbons wrapped in a ring, and 1 cyclopentane ring fused together. And we designate these A, B, C, D. The numbered carbons begin on ring A, and then you get 2 methyl groups at 18 and 19. And so we've got your nucleus. So if you see anything that has this format of putting these 3 cyclohexanes and 1 cyclopentane together, that thing is a steroid. Okay, if you see it anywhere, just know that. How do we number? We number starting from here at carbon 1, and we work our way around this way. I'm not going to have you name anything, so don't worry about the numbering system. Just worry about looking at this and making sure that you know that that means you're talking about a steroid. Cholesterol is the most important and abundant steroid in the body. It has a hydroxyl group on carbon 3, a double bond between carbons 5 and 6. So you can add, look, let's see, we're adding stuff. But do you see our nucleus? Our steroid nucleus? We got a cyclohexane, 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 cyclopentane. This thing's a steroid. Okay? And so this is cholesterol. Cholesterol, we say, oh, cholesterol's bad for you, right? Cholesterol's bad. So everything is bad for you if you have too much of it, right? Including water. And so we get cholesterol from meats, red meats, milk, eggs. It's made in the liver. We need it. You need cholesterol. You need it for your cell membranes. You need it for your brain and your nerve tissue. You need it to help form other steroids, like hormones in your body. And you need it for vitamin D. Right? But if you have too much of it, it can clog your arteries. And so you can see here's a normal open artery, and then you have an artery clogged by cholesterol plaque. Because we have these big nonpolar groups, right, that kind of maybe can stick together, and they're hydrophobic, so the water that's in our body is now washing them out. So, this is a nice little, look at that beautiful little conversion factor right here. So you may be looking at a patient's chart and you see that they have a cholesterol level in their blood plasma of over 200, right? So that's an elevated cholesterol level. Every patient, you know, is going to be a little bit different as to what's normal for them. It's definitely a genetic thing as well. But you know, you'll probably wind up having conversations with the patients about what they're eating and their cholesterol levels if they start to get too high. So if you're looking for foods, right, that are high or low in cholesterol, like if you eat bunches of beef liver, that's pretty high in cholesterol. Eggs are actually really high in cholesterol, which is a lot of people will eat egg whites and not the full egg because it's where the yolk is, where we got the cholesterol. Fried chicken, hamburgers, and then you got like margarine, which is why we make margarine, okay, because butter has 30 milligrams of cholesterol in a tablespoon, but margarine has none. Right? But of course the margarine's got other things maybe that I don't want, like trans fats. I don't know. I mean, there's a bunch of stuff as far as like health foods and things, but like just knowing that like, okay, you do need cholesterol, but we wind up eating too much cholesterol. So here's something like I'd ask you to do. I'd ask you, here's a thing, match all these groups. So pause and see if you can do that. Alright, so where's my carbon chain? Alright, so hopefully you said, hey, I think the carbon chain's hanging over here around D. This is my long carbon chain. Alright, where's my steroid nucleus? My steroid nucleus is everything in here, which is actually C. Where's the hydroxyl group hanging off? A. And where's my methyl group? You got a little methyl in your cholesterol hanging off at B right here. Okay? You don't have to memorize what cholesterol looks like, but I do want you to be able to break down the pieces organic chemistry style. So bile salts are something that's made in the liver and stored in the gallbladder. So if you have gallstones, those are bile salts. Okay, they're the solid. If your cholesterol levels are too high, you can get gallstones, which is not great. They have polar and nonpolar regions, and they're going to act like soaps. So they make fat soluble in water. That's their job. They help to absorb the cholesterol. But if you got too much, you're absorbing all of the cholesterol into these stones. And a lot of times we'll make these gallstones, and they're really small, and so they just are excreted from the body. But if you get too big ones, because you have so much cholesterol that your body's trying to absorb, you get big stones, and you try to pass those, and that's very painful. So here's a bile salt. Can you find the steroid nucleus? Can you see over here that I might have the remnants of, I don't know, a carboxylic acid and an amide, and you got an alcohol groups hanging off? Like, that's what I'm going to have you recognize. So this is a cholesterol ester. Okay, it's cholesterol, and then cholesterol has an alcohol group hanging off the end. I can form an ester bond with that alcohol on the end of the cholesterol, and I can make a cholesterol ester. They are how cholesterol is typically in our blood. Okay. So this is a lipoprotein. So a lipoprotein are complex things that we kind of use in our body to transport lipids, because lipids don't like water, so they're just going to like not go with the water. So we make them into lipoproteins so that the water can transport them. So what we do is we kind of shield the nonpolar parts from the water. So here's what a lipoprotein would look like. You get the phospholipid head, which is polar, right? And then you have your little cholesterols kind of sticking out in there. And look at the cholesterol ends that are hanging out of the polar surface. It's the OH end, right? Which is polar, right? The alcohol end is polar. And then I got some proteins kind of stuck in there. So you got these polar ends here, and all the non-polar ends are here. And so all of your triglycerides and cholesterol esters are going to be hanging out in this space, and you're kind of shielded by these phospholipid layer. And so this is kind of what soap does too. It kind of traps. It's like the Trojan horse, right? We're trapping all this non-polar stuff with this polar outside to trick the water into dissolving us. And so the water will dissolve all of these polar ends here, but it's not going to dissolve all this stuff on the inside that's a bunch of nonpolar stuff. So you get its core nonpolar stuff, outside is polar, and now we can transport them via water, right, which we need to do. So your lipoproteins are where we get your LDLs and your HDLs. So you got low density lipoproteins and high density lipoproteins. The package is what we're talking about here. And so if you're LDL, right, then you are lower density. And if you're HDL, you're a higher density. And here you can see here your percent by mass of each of the different lipids kind of gives you your different densities and cholesterol percentages. And this is just a little image of kind of how it works in the body. You're going to go more into that in physio for sure. And the last piece is we're going to talk about is steroid hormones. Hormones are messengers, right? And so when your hormone levels are a certain way, it's going to actually be sending, communicating things to your body. These are all produced from cholesterol. So if you don't have any cholesterol in your body, you can't make any hormones, and you won't be able to survive. You have to have hormones. So here's some different hormones that you may be familiar with. So you have structures of steroid hormones, and you can see in some of these hormones when we have the own ending, we got little ketones hanging off here, right? You got little ketones hanging out. You got an alkyne over here, and it's a triple bond. So as long as you can, you got a little benzene, a little phenol over here. As long as you can kind of recognize those things, you're good to go. I'm not going to have you memorize where they are and what the names of them are. So anabolic steroids, okay, they're all derivatives of testosterone. So we take testosterone and we like do some other stuff with it, some reactions with it, and change it around. They are used illegally to increase muscle mass. So if someone says like, oh, that person's on steroids, this is what they're talking about. It's one of these kind of things. It's not the ones that are just naturally produced in our bodies. It's these guys that are giving you a lot of the issues. Corticosteroids are ones that you may be actually prescribed to do something in your body, your doctor's prescribing you a steroid, right? It's typically a corticosteroid. We produce our own corticosteroids, but sometimes we need a little help. And they can do different things in your body, but we do need them sometimes from an injection or something to help out with an issue. And you, again, notice all the functional groups. That's what I really want you to be focusing on. And of course that steroid backbone, the steroid nucleus. Again, I'm not going to have you memorize these, but I will put a picture of them and I will say, what is this? And then lastly, one of the most important things that lipids do is they make up our cell membranes. We wouldn't have any cells if we didn't have lipids. So what we get here is we get this really cool phospholipid bilayers, we call it. So we have a phospholipid, so you've got your polar head here. These are your polar heads. So outside and inside, both jabbing with the water, okay, both polar. And we have your inside, in between these two, all of this area here is all nonpolar. So this is hydrophilic, meaning water loving, and this in here is hydrophobic, meaning water afraid. It's afraid of water. So it'll form this little layer, and then this gives us this shielding of our cells from the outside environment. And so I have different ways to transport through my cell membrane. I have diffusion, which is passive transport. Okay, higher concentration outside, lower concentration inside. It's just going to go through. You have facilitated transport. So maybe these little orange guys don't really jive with the nonpolar ends. Maybe they're too big, and so I get this little area for them to go through. It's called facilitated. Again, but it's still high concentration outside, low concentration inside, kind of guided. But then you've got this active transport, which is going the opposite way. It's kind of like reverse osmosis. It's like, hey, I'm going to go against the grain. I'm going to go from lower concentration inside, higher concentration outside, and I'm going to go this direction. You got to put energy in to do that, so we call it active transport. I'm not going to have you memorize the different types of the transporting from cell membranes. You will probably have to do that for physio though. So if you're super sure you're going on to physio, you may want to give that its own little note section. Talked about this. So here's the fluid mosaic model of the cell membrane. Like you get, it's not just the phospholipid bilayer. You've got like proteins stuck in there. You get side chains kind of hanging out. You get all these kind of other things chilling around in the cell membrane that allows you to just, you know, have the cell do its business. And because of the way that this is, right, your cell membrane is not rigid like a cell wall, right? It doesn't have that cellulose in there. Here's the definition of all your transports. Another picture of those transports that we just talked about, and a little study check of this again, not for me, but maybe for physio that you want to learn that. And then here's your concept map.